Welcome back to Coding with Qiskit 1. I'm your host, Derek Wang, and this is Episode 3, Hello World. What is Hello World? When installing anything new, whether it's a language or package, it's standard practice to include a Hello World example. The purpose is twofold. First, we ensure that the installation was done correctly. And second, we want to demonstrate what a typical application workflow looks like. Here, we're going to prepare a 2-qubit Bell state on a local simulator, and then to highlight how this approach can scale to utility scale circuits on devices with over 100 qubits, we'll generalize our approach. You can check out the tutorial on the IBM Quantum website linked below. In the case of Qiskit 1.0, it's been developed with Qiskit patterns in mind, a 4-step plan that many quantum computational workflows tend to follow. These steps are 1. Map the problem to circuits and operators. 2. Optimize the circuit. 3. Execute it on a backend. And 4. Post-process the results. Let's go through this step by step. So I'm going to pull up my Visual Studio IDE again, and we're going to create a new notebook. This one we're going to call, put in this folder here, the same one as last time, Episode 3, Hello World.ipy notebook. Okay. So in this very first step here, we're going to do the Hello World example on a 2-qubit Bell state. And the very first step is going to be to map the problem to circuits and operators. Okay, so let's change this cell to code. Oh, and let me also actually change the kernel to the CWQ Coding with Qiskit Python environment that we generated before. To generate the Bell state, you apply a Hadamard gate on the first qubit and then a CNOT. The Hadamard on the first qubit puts it into a superposition of 0, 1, and the CNOT results in the entire state being 0, 0 plus 1, 1. In Qiskit, you can do it this way. First, we're going to import the quantum circuit, and then we're going to generate one that has 2 qubits on it. From here, let's do the Hadamard gate on the 0th qubit, followed by the CNOT gate between the 0 and first qubits. And then we're going to draw what this looks like here. And you can see that's exactly as we expect it to look like, and this is how we would generate the Bell state. The second part of step 1 is to map the problem also to operators. In this case, just to make sure that everything is working the way it works, we're going to be measuring the expectation value of some 2-qubit operators and some 1-qubit operators. In the case of this Bell state, one can straightforwardly see that, for example, the ZZ or the XX operators should have a non-zero expectation value, while the single qubit ones like the ZI, IZ, XI, or IX, meaning Z operator on the first qubit and an identity operator on the second qubit, should have a 0 expectation value. And this is going to be the signature of entanglement in this particular case. So let's create those operators so that we can measure them using our backend. So I'm going to import these Pali operators, and I'm just going to create some Pali operators like so, where I pass in the string for each one. So, oops, this should be Pali here. So ZZ equals Pali string ZZ, and I'm going to do the same for a few more, just by way of example. So ZI equals Pali ZI. Let's do the same for IZ. And now let's make the 2-qubit XX operator and do the same for the X single qubit X operators. Let's look at both of those as well. Okay, now we create the operators, and now let's just put them all into a list so that we can pass them all at once later on to the backend. Yes, there we go. Okay. So the observables have been created now. Step 2 of the Qiskit patterns workflow is to optimize the circuit observables. In this case, because we are going to run this all on the local air simulator, there's nothing really to optimize. We don't need to map this to some local connectivity or the native gate set of the backend, because the air simulator can handle all of these things. So for now, we'll skip this step, but I'll show you what we can do when we go over to the 100-qubit example. In step 3, this is where we're going to execute on the backend. So how are we going to do this? First, we need to instantiate our air simulator and then generate a way of accessing that simulator through the estimator primitive. So I'll show you how to do this now. And in a future video, we'll talk more about the primitives, how they're structured, how we can kind of fine-tune their configuration. But for here, we're just going to instantiate it. So what I'm going to do is I'm going to import the Qiskit air primitives estimator, like so, and see if that works. Okay. So in this case, they didn't find the module Qiskit Air, and that's because earlier when we were doing all these installations, I didn't install it at the time. So what I can do is open my terminal again, or even do it from the Jupyter Notebook if you'd like, and I'm going to make sure I do this installation. And this is a pretty normal thing to happen. You think you have a package, but you don't. So first, again, I'm going to activate my CWQ Python environment. And from here, I'm going to do pip install. Remember, anytime I install a package, I want to make sure I use pip install Qiskit Air. And it handles it in a few seconds. OK, good. That's taken care of. And every time you install a new package, you want to make sure that you restart your kernel so that it knows to call this anew. And let's rerun these code blocks. Great. This time, Qiskit Air ran successfully. So now we have access to this. So now let's instantiate this estimator like this and run a job with the run function where we're going to pass the quantum circuit and the observables. If you take a closer look at how we pass these things, you can see that I actually had to multiply the number of quantum circuits by the number of observables. And this is just to make sure that we have the same number of circuits as observables. And this is because in this particular case, the input format for this version 1 estimator that's what it asks for. But you'll see later on in the utility scale example that V2 primitives are a lot easier to work with. And so we'll be using those for the rest of the study. But for here, for the air primitives, we're going to be using this version 1 with this particular input format. Now that this job has been run, do an equal sign here, we're going to print out the result like that. So let's just run it. And almost immediately, we can see the results come out for the expectation values for the 6 operators I had earlier. So step 4 is now to do the post-processing and plotting. In this case, there's not much post-processing to do because the estimator handled a lot of that for us automatically. So we'll just do the plotting here. I'm going to import matplotlib.pyplot as plot. And then I'm going to create my data labels. So remember, it's the ZZ, ZI, IZ, XX, XI, and IX. Oops. There we go. And then now I want to get the values associated with each of them. And to do that, I can do job.result.values. And then I'm going to plot everything. So I'll do a plot of the X labels being the data I just defined up there, the values, and let's give it markers for each step. OK. Give it an X label. It's good practice to always label your axes. We'll call this the observables. And then Y label, we'll give it the expectation values. And let's show the plot. So there you go. As expected, for this 2-qubit entangled state, we get expectation value of 1 for these 2-qubit correlated observables. And then for these single qubit ones, we get an expectation value of close to 0. They're not quite at 0 in this case because probably due to shot noise. OK, so that is the 2-qubit example. Now let's kick it up a notch and go to the 100-qubit utility scale example and show that we can use the same exact process, patterns, and tool set to now work at this much larger scale. So let's make a new section of this notebook called, what do we call the first one? Oh, Hello World on 2-qubit. So now let's extend the Hello World example to an n-qubit GHZ state. So the n-qubit GHZ state looks a lot like the 2-qubit Bell state we just prepared, which is a 0, 0 plus 1, 1 superposition. In the n-qubit GHZ state, it's going to be 0, 0, 0, 0 plus 1, 1, 1, 1, or as many zeros and ones as there are qubits in your system. In this case, I want to be able to have my workflow be flexible for the number of qubits. So I'm going to write a function for this actually in this mapping step that allows me to change the value of n. So let's do that first. We're going to map the problem to circuits and operators like before. And this time we're going to write a quick function that allows us to make circuits for any value of n that we want. So let's call it get the quantum circuit for n qubit GHZ state. And we're going to have this input be n. So it's going to look pretty simple. Quantum circuit is going to be, QC is going to be a quantum circuit with n quantum registers. We'll apply the Hadamard gate to the 0th qubit, just like before. And then for the rest of the qubits, we're going to apply a ladder of C0 gates. And it should be pretty straightforward to see why that should then create the state 0, 0, 0, 0 plus 1, 1, 1, 1. So let's do it this way. qc.cx I to I plus 1. And then return qc. And let's make sure that this function makes sense here just by drawing it for some value of n. So let's set n equals to 10 for now. QC equals get QC for n qubit GHZ state. We pass in this n, and then let's draw it. There you go. It was really fast, and now you can see that we have a 10 qubit circuit, Hadamard on the first or the 0th qubit, and a ladder C0s all the way down. And you should be able to see that this should result in a circuit that results in the n qubit GHZ circuit. In step 1, the first step is, of course, to do mapping to circuits, but we also want to map to the operators of interest. So in this case, what I'm curious about is, let's say you're curious about how noisy your large-scale device is. One way you could probe this is by looking at correlations between qubits as they increase in distance from each other. You would expect that as the qubits get farther and farther away from each other, that there's more and more noise between them, and maybe your expectation values are more affected or corrupted by this noise. In this experiment, the way we can handle this is by looking at the ZZ operators between qubits as they go farther and farther away. So we would expect the ZZ operator between the 0th and 1st qubit to be the smallest, and then between the 0th and 2nd qubit to maybe shrink or be more corrupted by noise, then the 0th to the 3rd, and all the way from the 1st qubit to the very last qubit. So I want to create operators that basically allow me to probe this increasing distance, and then I'll eventually look at how maybe the expectation value is corrupted more and more as this distance increases. So let's create those operators now. So I'll do qiskit.quantum_info import sparse polyop this time around, because we're going to have large sparse poly operators that might take up a lot of space. And let's first define all the strings that correspond to these operators. And like I said, it's going to be a Z operator on the 0th qubit, followed by some number of identity operators, followed by another Z operator, and then we're going to fill up the rest of the observable with identity. So it's going to look something like that. And then just to make sure that everything came out correctly, we're going to print out these operator strings and then print out the length of the operator strings as well, because we expect this for n qubits to have n minus 1 of them. And then I'm going to create the operators using this sparse polyop function that takes in each string, operator string, for operator string in operator strings. Great. Hit enter. And indeed, you can see that we have these operator strings that start with ZZ right next to each other. And then there's more and more distance between them until the very end, where we have one at the beginning and one at the end with identities in between. You can also see that we have 9 of them total, which makes sense because we have n total qubits, or 10 total qubits in this case. And just before I move on, what I'm going to do now is actually just change this n from 10 to 100 so that we can get the 100 qubit circuit. I just chose 10 at first for visualization purposes because this picture is about to be quite large. Yeah, you can see it's huge. And we got this large 100 qubit ladder going all the way down. This is onto the next page already. Yep, so it's a pretty large circuit there. All right. So I'm going to just skip all the way to the bottom, regenerate the operator strings. Now you can see that there's 99 of them, and that makes sense. Okay, so the next step of this is step 2, where we want to optimize this problem for quantum execution. So let's label the section step 2, optimize the problem for quantum execution. And we're going to, in this case, transpile the circuit for the backend such that it matches the local connectivity, native gate requirements, and if we want, we can merge some 2-qubit gates or something like that. In this case, I don't want to do that. In this case, I'm going to do a very simple transpilation that doesn't take up much classical compute time, but a lot of the expertise in quantum computing does come in this step, where you can use, say, symmetries of the problem, prior knowledge, to make the circuit as easily executable as possible. So in this case, I'm going to first call my backend and then use the backend to get all the configurations from the backend to tell my transpiler how to convert the circuit into something that can be executed on the device. To do that, I need to import the Qiskit runtime service, which will then allow me to access the backend. And I also want to generate a preset pass manager based on whatever backend I import. So the backend in this case I want to use is IBM Brisbane. The one I pointed out in the last video, actually, is a 127 qubit device with pretty good performance. And then I'm going to get this backend like this by passing in the backend name here. And then I'm going to create a pass manager using this generate preset pass manager function, where I can tell it the optimization level. In this case, I'm just doing simple optimization, set it to 1, and then pass in the backend here. And this will then populate the method with everything that needs to be known about the backend, like the connectivity and the native gates. With all this, I can now transpile my quantum circuit, QC underscore transpiled equals pass manager dot run. Oops, typo. Pass manager dot run, and I will pass in this quantum circuit that I built before. And then I need to do the same to the operators. In this case, what I'm doing to the operators is that originally I created them in order of 0 to 100. But when you map the quantum circuit to a device, now all the indices get swapped around. So what this method takes care of here is just making sure that the indices of the operators get mapped to the right points on the transpiled circuit. So we'll just do, for each operator, we're going to apply the layout of the transpiled circuits layout, and like that. So now we're calling the service, pulling in the backend information, generating the pass manager, and creating the transpiled circuits and operators. Great, that's done now. Now for step 3. In step 3, we want to execute on the backend. So here, okay, let's change that to code. On the backend, we're going to initialize an estimator that takes in the backend, and where we can also configure some basic properties about it, whether we want to use error suppression, error mitigation techniques, how we do the transpilation, things like that. I'll talk about these in more detail in the next video. In this case, I'm only going to set the bare minimum parameters just so you can see how it works overall. So what I need to do first is I need to, again, from the Qiskit IBM runtime package, import the estimator. This time I'm going to import the estimator v2, which makes submission and looking at results a lot more intuitive. And then we're also going to import this options function. And that will allow us to configure exactly how this operator behaves. So again, let's first define the options like this. And you can see all the possibilities in the documentation, but for now, I'm just going to set a few simple things. I'm going to set the resilience level to 1. That just means we use measurement, readout mitigation, and simple things like that. You can set resilience level to higher values as well. At level 2, for example, you get zero noise extrapolation, but that's something we can talk about in the next video. Then I'll do options.optimization level equals 0. And this is because I already did the transpilation on my local device. And finally, because the quantum circuit likely has a lot of idle times that you might have seen when I showed the 100-qubit version, I'm going to use dynamical decoupling. This basically inserts some pulses into the idle time to help us get rid of some of this crosstalk and other coherent errors. So I'm going to first set it to true, and then I'm going to set the sequence type to XY4, which we've had good experiences with in the past. Okay, so now the options are set up, I can start to generate the estimator. So the estimator object is going to be based on the backend and the options I just defined. And finally, I can run a job by doing estimator.run and passing in the quantum circuit and the operators that we generated before in step 2. Let's get the job ID and print it. Okay, so let's send this off now. Oops. Let's see. The length of pub must be 2, 3, or 4, but I gave a length of 4,400. So there's some bug here. I wonder what I did wrong. Oh, I see what I did. So they expect to get past these kinds of tuples here, so I need to do that. Let's try that again. Great. So you can see that I just got this job ID. Now what I can do is go back to the IBM Quantum website and actually see my job in the queue. So there's my job right here, the CQ, SN, etc. It was created just less than a minute ago. It's IBM Brisbane, and there isn't a wait time yet. So just so we don't have to wait, it turns out that I've run this exact job already with the exact same settings. And so now we'll just call that particular job, and so we can plot the results now. So in step 4, we're going to do the post-processing and plotting, just like before, same exact process. Okay, so the job ID from before, I'm just going to copy and paste it over here. So the job ID that I got before is this. And so now I can retrieve the job by using the service and then putting the job ID into this job function. So now I should have the job. Oh, did I not create the service at any point? I see. Because over here, I just used it directly. I never created the service object, so I can just do that here. Qiskit runtime service, and then try this again. Okay, we got the job. Now let me do one last thing, is to plot it. Import matplotlib.pyplot as plot, and plot this really quickly. So scatter. I need to define the axes first. So let's define the x-axis as the distance between the z operators. So for the very first one, it's going to be the distance is 1 from z0 to z1, and then it'll go all the way up to 99 in our case. So I can write that pretty simply like this. Yep. Too many brackets? No, just enough. And then I also want to get out the expectation value at each of those. So we'll call this. I'm putting in the 0 index here because we only passed one set of input circuit observables, and so that corresponds to the 0th result. And then the values will just be result.data.expectation values. And because I care about how these expectation values decay with distance, I'm just going to normalize it by the 0th one, where I expect to see the highest magnitude of expectation value. Now I'm ready to do some plotting. So I'm going to do plot.scatter, put in the x-axis, the y values, the marker, and then finally, let's label this 100-qubit GHZ state, making sure we label the axes. And let's do this as let's call this the Z0, ZI expectation value normalized by the Z0, Z1, which are the closest ones together where we expect to see the highest. Yep, I think that makes sense. And then make a legend and show it. Okay, and then we have our plot. You can see that as the distance between the qubits increases, the signal decays over 10 or 20 qubits for this 100-qubit GHZ state. So we actually have works where we show that when you're a lot smarter about the transpilation, the error suppression, mitigation, by toggling different settings in the sampler and estimator primitives, you can get much better results. But in this case, we just wanted to show a really quick example of this utility scale quantum computation workflow that's enabled by Qiskit. So there you have it, a hello world example for Qiskit, where we show the application workflow for running a 100-qubit circuit on real quantum hardware. In today's live coding examples, I skimmed over some important details concerning the access model with primitives. In addition, we studied a quantum circuit that is pretty straightforward to predict the exact output of, partially because it contains only Clifford gates, meaning that the circuit is easy to classically simulate. Next time, we'll bring it up a notch. We'll look at how primitives can streamline the execution of utility-scale quantum circuits that are hard to simulate. Thanks for watching, and we'll see you next time.